Hi, in this video I want to describe how to determine whether a molecule is polar or nonpolar and discuss their relative water solubilities. There are very easy analytical ways to determine whether a molecule is polar or nonpolar relative to another molecule. This is very important in terms of tracking reactions to see whether you've actually changed the identity of a molecule, changed their functional groups. For instance, if I have this molecule here, something like that, what we can do is we could add more carbons to this carbon here by first removing a hydrogen and making it an anion. So for instance, if I use a very strong base, such as CH3-, what I could do is make the anion. So there's 3 hydrogens here. We remove one of the hydrogens with the base, and we now have this anion right there. Now the details of this reaction you don't have to worry about now. What you do want to realize is that, well, first of all, we have a carbon anion, so we have a lone pair there. Let me do that. Let me add all the lone pairs. Okay. What I want you to focus on is that we changed the molecule by giving it a formal charge. We made it a C-. And then what we can do is add an alkyl group via an alkyl halide, and we have this. So what if we needed to, is that correct? We have this carbon here, and I added these 2 carbons. Again, don't worry about the details of the reaction. Worry about, do you know the relative polarities of each of these molecules? If I'm trying to do this sequence of reactions, it would be very useful for me to track whether I am changing the molecule. And we could do that very easily by polarity. So if I take a look at this molecule here, if I'm asked to determine its polarity relative to other molecules, I want to identify any bond dipoles. Oxygen is electronegative, so it automatically gets a partial negative. Okay, and it's pulling electrons towards it, so it's pulling electrons away from this carbon, which is partial positive. So there's a permanent bond dipole. Whenever you have what's called a heteroatom, which means it's not carbon or hydrogen. In organic chemistry, most heteroatoms are going to be nitrogen, oxygen, sulfur, phosphorus. That heteroatom typically adds polarity. So atoms like O, N, S sulfur, F phosphorus, and the halogens. What are the halogens? Fluorine. So we're going down the column. Let me see if I have my periodic table. I hope so. Here we go. Halogens, or some people call them halide atoms. Fluorine, chlorine, bromine, and iodine. Okay? Those atoms, fluorine, chlorine, bromine, iodine, along with the nitrogen, oxygen, sulfur, phosphorus, those are electronegative compared to carbon and hydrogen. They pull electrons towards them when they're bonded. These are all the partial charges that should be added to this molecule. And we have one bond dipole, the carbon-oxygen double bond. So that adds polarity. versus if this oxygen wasn't here. Maybe if it was a carbon, a CH2 group, that would be less polar than this. So again, we're adding polarity. The other thing you want to remember, especially in organic chemistry, is that the carbon, hydrogen, and carbon-carbon bonds will be considered nonpolar. The more carbon-carbon bonds and the more carbon-hydrogen bonds you have relative to the heteroatoms, the more nonpolar the molecule is. So I'm not going to give a ratio. Okay, with experience and more practice in the lab and in the lecture, you'll know how to determine whether we have enough bond dipoles to make the molecule polar enough for it to be soluble in water. But let me just write here, the more CH and CC bonds, and that could be a double, single, or triple bond, relative to the number of heteroatoms. Okay. The more nonpolar the molecule is. Does that make sense? If a heteroatom adds polarity, then the absence of heteroatoms and the presence of a lot of carbon and carbon-hydrogen bonds, that will make the molecule nonpolar. Right? More of these polar, more of these relative to heteroatoms, more nonpolar. Okay. There's one last thing I want to add before we get back to these molecules, is that simply the more polar a molecule is, the more soluble it is in water, and other polar solvents. Okay. Oh, actually I wanted to add one more. This will be the fourth bullet point. 1, 2, 3, and 4. If adding a lot of heteroatoms that creates these bond dipoles makes a molecule more polar, putting full charges, putting formal charges, will make the molecule even more polar. So full charges create larger dipoles than these partial charges, right? These are called partial charges. This lowercase Greek letter d, delta negative, delta positive. Okay. What did I just say here? Formal charges add even more water solubility, add even more polarity. So formal charges, versus partial charges. Adds more polarity. Okay. So taking a look at our three molecules, we could run this sequence of reactions stepwise, and we could create this molecule. We'll call this molecule 2, molecule 1, and the final product, molecule 3. And like I said at the beginning, there are ways to monitor the polarity of your molecules in a sample. There could be a mixture, right? If we run this halfway, we'll have a mixture of 1 and 2. But there are ways to observe what molecules you have in terms of their polarities. Now take a look at this molecule here. What do we have? We have partial charges, we have a partial negative, we have a partial positive. Let me add all my lone pairs again. and we have a full charge, and we have a full formal charge, right? What happened here is this C minus picked up this hydrogen and took it away from this molecule in an acid-base reaction. Between these two, I would predict 2 is more polar than 1. Because not only do we have the bond dipoles, we have a formal charge. And the number of carbons are equal between these two. So with all things being equal, adding formal charge makes the molecule more polar. So one way we could indicate that is 2 is greater than 1 in terms of polarity. Okay. In this second reaction, what happened here? That carbon attached to this carbon and kicked out what's called a leaving group. Again, the details of the reaction are not important. What's important is you focus on the actual products, and here the intermediate. So in this case, we still have our bond dipole. Okay. You notice that I'm not putting any partial charges on the carbon that's involved in carbon-carbon bonds, right? This positive, partial positive, is because of this partial negative oxygen. Because again, we're going to consider all carbon-hydrogen and carbon-carbon bonds nonpolar. Technically, if you remember your Gen Chem, consider nonpolar or covalent nonpolar bonds. Or let's say nonpolar covalent bonds. Let's take a look at compound number 3. We have that bond dipole. We no longer have the C minus, but look, we added more carbons. We added more carbon-hydrogen bonds and carbon-carbon bonds, thus decreasing its polarity compared to 1. We lost a formal charge. We added more carbon-carbon bonds. So, really, relative to molecule 2, molecule 3 is nonpolar. This is the most nonpolar molecule out of these 3. And your trend would look like that. 2 is the most polar, followed by 1, and then 3 because we have added carbons, but we didn't really add polarity. We didn't add any heteroatoms. Then 3 is the most nonpolar, or you could say the least polar. Now, how do we connect this to water solubility? The more polar the molecule, that's supposed to be an S. The more polar molecules, the more soluble it is in water and other polar solvents. Another polar solvent could be something like methanol, CH3OH. Okay. So while this is the most nonpolar, 2 we would say is the most water soluble. Okay, so go ahead and see if you could do these problems that you need to rank the water solubility, understanding that the most polar is the most water soluble, and using these 4 bullet points.